Let's begin the study of the understanding, the progression of astronomy from antiquity up to our current modern understanding. And the roots of all this is known as archaeoastronomy, the ancient astronomy, like Stonehenge, shown here, the ruins of Stonehenge. Now, one thing that's for certain amidst all the uncertainty about what the archaeo sites really revealed in terms of science, what the peoples associated with that really knew, lots of debate over that. But in essence, it's keeping track of the seasons, which are really important for their life, special sun events, timing. So that was a lot of what they did, even though their culture may have spent a lot of their total energy invested in these things at times. But it's very difficult to understand just exactly what they knew and what they didn't know. It gets really interesting with the ancient Greeks. I mean, by 3000 BC, we had advanced civilizations established in Egypt, Mesopotamia. The pyramids were already built by 2100 BC that were carefully aligned with the cardinal directions north, south, east, west. So there was a lot going on there, and that's a study of its own. But much of science, as we know it currently, arose in Greece, and we're talking about 500 BC. Greek science was characterized by something that was uniquely different than what preceded it. 4 points, namely that they minimized the supernatural, to use mathematics to get specificity, reason from observations rather than just philosophy, and produce models of nature that actually replicated the real thing. So I just want to point out a few key people, and we'll just fly through this. We had Thales, 570 BC, who came up with the first natural model of the universe. Anaximander proposed that the Earth floats in empty space, and that's really not too bad because it kind of does. And he's given credit for the idea of the celestial sphere, which we've already been introduced to. Pythagoras, in addition to the Pythagorean theorem, he has argued that the Earth is a perfect sphere and that the Earth is the center of that celestial sphere. Plato, you've all heard of Plato, 370 BC now. He really argued strongly for objects moving in perfect circles because geometry is perfect, and there was a perfection of the heavens that was a bias in the Greek thought. In fact, it was thought more than data that drove his underlying statements and philosophies. Eudoxus, 360 BC, he had spheres within spheres to begin to match reality a little more closely. Then we arrive at the powerhouse, Aristotle. So Aristotle had a huge impact on the assumptions and the beliefs of the time, the paradigm of the time. He argued very powerfully for an Earth-centered universe, that where we have a imperfect and changeable Earth, but out in heavens they obey their own laws, and things are perfect out there, described by perfect spheres. Gravity pulling heavy things to the center of the universe, which is basically the center of the Earth. Lighter things floating to the heavens, like fire, air. So he maintained and strongly promoted a geocentric view, which amazingly, especially from our current understanding of how fast things change, 2,000-year dominance of this geocentric view. Heraclides suggested that the Earth rotates. That was a pretty big step, especially even up to this present day. You go outside or you stand on the Earth, it doesn't seem like the Earth is moving. So there is an intuitive sense that counters what we currently know to be reality. Aristarchus suggested the Earth goes around the sun all the way back to 250 BC. That will turn out to be important in the thinking of Copernicus much later. So Earth going around the sun, that's a heliocentric idea. He didn't get a lot of press, so to speak, in his day on this idea. Eratosthenes, really important measurement that he made. Estimated the circumference of the Earth very well, in fact. It was an amazing feat that he did with shadows and sticks at noon in two different places, 800 miles separated, and actually correctly determined the circumference of the Earth. Apollonius, multiple circles, explaining retrograde motion, which we'll discuss shortly. Hipparchus discovered precession. We've discussed that before, so you know that they were making really careful measurements to discover that particular phenomena. Also invented the magnitude scale, the relative brightness of the stars. Ptolemy, another big player in the history of astronomy. He synthesized everything that was known before and worked hard to come up with models that were in agreement with the observations. He was a stickler for that. His model was in use for 1,500 years with modifications, but nobody was able to get beyond his model, do any better. So obviously he did a lot of work with this. And in brief, in a nutshell, here it is. We have Earth at the center, Moon going around Earth. In fact, everything's going around Earth. And we've got the planets in their own little circles called epicycles, with a fixed sphere of the stars in the background. So here's a little more detail on one of those orbits, and there's names associated with these things, and it starts getting complicated when the Earth isn't at the center, but you have this epicycle, and the bodies are circling around that as they're circling around the larger orbit. There were some thorny issues associated with Greek astronomy. In the Aristotelian universe, it was understood that the Earth did not move. And in fact, an experiment that seemed to validate that was the fact that they could not detect any parallax. Well, first of all, what's parallax? If you would, for a moment, either pause this video or just do it now, hold your thumb up to the wall and cover a clock or a picture or some spot on the wall or a light bulb with one eye open. Okay? Now, switch eyes. Do you notice the apparent shifting of position of your thumb with respect to the object you are covering? That's parallax. You're observing the object that's in the foreground through a different angle, so it shifts its position with respect to the background. Now, when it comes to Earth, we have a Earth rotating around the sun. If it did, the argument went, then as this Earth rotates around the sun, we should have a different view in July of this object, this foreground object compared to the background, than we do in January. We're going to see a different view. Here's the view in July, and in January, this foreground object shifts its position with respect to the background stars. Well, no parallax was observed, and that seemed to be an argument that the Earth did not move. So that was kind of thorny. Turns out what they didn't know is the stars were so far away that the 93 million mile radius of Earth around the sun was insufficient to enable the technology of the day to pick up any parallax that was actually there. Another issue is this funny wanderers, the stars up there that move around and do things that the other stars aren't doing. And they call them the planets, where there's this retrograde motion, this motion where it's going in the normal direction and reverses and loops around and continues to go. So that's going to turn out to be a huge issue that needs to be resolved, because you got to match your model with the reality out there in nature. Here's a simulation of that, and this is called a retrograde motion. Notice the ecliptic in here, and this is Mars, and it's near the ecliptic, and you're seeing over a period of months the funny, strange motion. Instead of just moving eastward, it moves westward for a while and then stops and moves eastward again. Very strange. Well, it's a problem. Problem is, in the Aristotelian universe, that strange motion was hard to reconcile with perfect circles, which were part of the philosophy. So here's a nice point-by-point rendering of Mars in a 2009 retrograde loop. And again, Here's the normal motion of Mars, taken 3 days apart. And then it kind of, well, it stops and reverses direction in the sky and goes the wrong way. And then starts going the correct way again. So how do you make sense of that with perfect circles? You can see, just looking at this, it doesn't look very circular, does it? The Ptolemaic system of epicycles could take care of this in part, not very well, but it was able to account for this problem. So the solution is epicycles. And so here we see the orbit of the wanderer, the planet around the Earth. But that's the main orbit, but here's this epicycle, and if you think of the planet actually spinning on this thing while the whole epicycle is moving around, you actually can get the planet itself to follow this retrograde path. So that worked reasonably, but it's pretty darn complicated, and there's no real reason why you should have these epicycles. Where do they come from? What produces them? Here's a little animation of just kind of showing that wheel within the wheel and how it can produce motion when you line up Earth with the planet. You can see that you get this backwards motion. So that's what we're talking about. Well, the epicycle system by Ptolemy was the reigning paradigm, the model of this millennia. 1.5 millennia, 15 centuries. And it was the standard model of the universe until the Copernican Revolution, which we turn to next. The Copernican Revolution actually had its foundational roots in the Middle Ages from Muslim and Hindu scholars and their efforts. Well, there was the unfortunate event of the destruction of the Library of Alexandria, the center of knowledge for the entire world. And a lot of the Greek works were lost. Most of knowledge was lost at that event. That was a really huge turning point in world knowledge. But the Muslim and Hindu scholars were able to save some of the Greek works and also some of the knowledge that comes from China. They developed mathematics and astronomical instrumentation. So there was some stuff going on with astronomy during the Middle Ages. And then the birth of modern science, which is considered to be taking place during the European Renaissance, 1400s to the 1600s. The also very influential event of Constantinople being destroyed. The Eastern scholars went west to Europe, and that knowledge that they carried with them helped ignite the European Renaissance. Well, Nicholas Copernicus, mathematician, lawyer, economist, physician, cleric, within 50 years began to put together all this information and had insight and mathematical basis for overturning the Ptolemaic Earth-centered universe. And because he was able to do this, that is indeed a revolution. Well, interestingly, he unearthed the sun-centered work that Aristarchus did 1,700 years earlier. Remember, 250 BC, I think it was. And that was a key part of the direction that he was going with his cosmological models. He found the distances and orbital periods of the planets, and as he studied those particulars, it convinced him of the validity of the heliocentric theory. Produced a work called I'm not going to try and pronounce that, but you see it there on the screen. And May 24th, 1543, he published his great works on the orbits of the heavenly bodies. His heliocentric universe of Copernicus. So here's the Ptolemaic system with retrograde loops, epicycles. The Copernican system was much simpler in principle because it didn't require all that complex nested circles to reproduce this retrograde motion, because it follows naturally from heliocentrism, where here we have Earth moving faster, Mars moving slower, because it's based on his observation of the data, but also we know that Earth is faster because gravity tugs on it harder than Mars. So he had all this right. And basically, the resolution is that as Earth is in its orbit and Mars is in its orbit, Earth is going faster than Mars. So if you look at this line here, Earth starts overtaking Mars. But based on the angles, it looks like Mars is still moving eastward. But then as Earth catches and passes it, it appears as though Mars, keep drawing the line from Earth to Mars, and you see it go retrograde and then back again. So if you follow each one of these lineups, you can see how basically like two people running on a track, and somebody on the inside lane is passing someone on the outside lane. Suddenly it looks like that slower person is reversing their direction from the point of view of the faster person. It's another way to think about it. So it made Ptolemy's Epicycles unnecessary, but it didn't get a lot of traction. I mean, a model that's been in place for 15 centuries is not easily overturned. And the biggest problem was that the Copernican method Copernicus did not want to release control of the idea of perfect circles. And because of that, the predictions that his model offered were essentially no better than the refined Ptolemaic Epicycles system. And so, I mean, why should we completely transform our view of the heavens when your model doesn't do any better than the Ptolemaic model, Copernicus? So that was a problem. The Copernican system, the heliocentric system, was a revolutionary idea in terms of its natural simplicity, ease of reconciling the retrograde motion of the planets, but it begged for validation. And so we have the best data on Earth needed to impose upon the theory to establish it. And that was given by Tycho Brahe, a Danish noble who had favor with the king, who built him an observatory on the island of Sven, and he built some of the most impressive naked eye astronomical instruments that the world has ever seen. So this was a crucial part of the development. The instruments he built were 10 times better than any had ever been, so he was able to take data to 1 arc minute of precision. An arc minute, 1/60th of 1 degree. He could not detect stellar parallax, as we discussed, so he thought Earth must be stationary, but he thought everything else orbited the Sun, which was not a very popular model. So here's his model, the Tychonic system, and we have the Sun orbiting Earth, but everything else orbits the Sun. So you can see all the planets orbiting the Sun. The Moon orbits Earth, and the Sun and all the other planets hooked to the Sun essentially orbit Earth. It's a really strange system, but that's what he thought probably represented reality. In 1600, he hired a guy by the name of Johann Kepler to make sense of all the data, because he wasn't able to do so, and he needed a really good mathematician to basically prove his particular version of the universe as it was understood and solve the mystery of the heavens. On his deathbed, Tycho Brahe was purportedly said to Johann Kepler in 1601, "May it not appear that I have lived in vain." And Johann Kepler was certainly determined to make good on that, but he wanted to get the data that Brahe had amassed over almost 30 years of careful observing. And this is going to lead to a revolution in our understanding of the universe. Here's just a couple other instruments that Brahe made. He made some really complex and interesting devices. But let's go on now to part 2 and finish the story.